Let f be differentiable. The table below gives values of f and f prime. So differentiable means nice and smooth. You know, there's no holes or breaks, or it's not jumping around. So it's so basically in a table. So f being differentiable would mean f prime exists everywhere. It means f is nice and smooth. Now it doesn't mean f prime is smooth. F prime could actually be sharp. Right, but it has to exist everywhere, so it can't be any holes and stuff like that, but it has to exist everywhere. The line tangent to the graph of f and parallel to the segment between the endpoints intersects the y-axis at the point blank. Okay, so what do you think? What would your first thought be here?
Tangent lines.
Why?
Because it's parallel to the segment, so if you connect the two endpoints.
But why would that be horizontal? I mean,
it could be.
Yeah, because negative 2, 1 could be here. Yeah. But wouldn't plotting them be a good idea? I mean, to me,
you get the slope.
Right, that's what I'm thinking. I mean, here's the segment between the two endpoints, right? Got a bunch of points in between. Oh, oops, that's not right. I just plotted that prime. Negative 2, 26, right? And 10, 2. Right? And so can't we do that slope right there? So that'd be 24 over 12, which is 2. The line tangent to f and parallel, negative 2, yes. Parallel to this segment. So a tangent line, so somewhere in here, remember the mean value theorem? If the function is differentiable between the endpoints, continuous, in the closed interval, then there's some point. So if this curve's doing this, there's some point that has that same slope. So it says the line tangent to this graph and parallel to this segment. So we need some place where f prime is negative 2. Well, right there, right? So where's the place where f prime is negative 2? Right there, at 4. So what does this tell us? Intersects the y-axis at the point. Okay, so what do we want to do now? Tangent line. Yeah, that's what we're talking about. The line tangent to the graph right there. Right? The line tangent to the graph. We're talking about tangent line anyway. So what do you need? You need the slope, which we just got, and you need the point, which they give you. Is that right there? Right? So that's y equals negative 2x plus 8 plus 23 would be what, 31? That's the tangent line. So where does that cross the y-axis? It's hard to read now. Where does this line cross the y-axis? At 0, 31. Just an interesting way of asking that question with different information, but it's the same thing. It's the same thing we always want to do when they talk about the tangent line. You can slope and a point. They talk about the tangent line is parallel to the segment between the endpoints, so we draw the two endpoints. I mean, I wouldn't have had to draw those. We could have just done the slope. We could have just done the slope between those 2 points right there. I mean, right? I wouldn't have had to draw it, but just need the slope between those two. Okay? What else? Rectangle to be inscribed in a semicircle of radius 8. What is the maximum possible area of the rectangle? So it's always good so if you want the maximum area of the rectangle, we're gonna wanna write the area of the rectangle. Well, the area of the rectangle is like that width. I think a lot of times it's good to put it on an axis here. You may not have to do that. Maybe, you may not have to do it, but it says radius 8. So maybe you don't have to. If you want to do, it's inscribed in a semicircle. Let's look at it. Okay, so here'd be a semicircle of radius 8. So this whole thing would be 16. Here'd be a rectangle that would be inscribed in there. Okay, so you could do that. I mean, so now we could label a couple different things. We could label, I don't know if it'd be easier to do an equation in that semicircle. Okay, it says one sideline on the diameter of the circle, so that's how we know this right here. Okay, so we're going to want to label, if we label that our width, label that W, and we label this our length. We know it's 16 all the way to there. Okay, how could we, so that's our areas, length, height, width. Remember doing max problems, they said, we always said you had to find another way. You needed some secondary equations to try to get that down to one variable, right? Because what could happen is you could have a lot skinnier looking. You could have way out here, be longer but not as tall, or you could have it way in here, right? Be taller but not as wide. And so somewhere in there would be the max area. So what do you guys think? What would be some? So you call these little pieces x. So L plus 2x. Now the only thing I'm thinking about that would be you've introduced another variable in there, haven't you? How would that relate to W, I guess is what I'm saying. I mean, I think that's a true statement. Did you do anything more than that, or are you just thinking out loud? Yeah, I mean that's a true statement. I'm not sure how it helps us. Here's what I think. Here's what I think would help us. What do we know about that? Isn't that 8? So what can you tell me about this right here? Say that again. Well, I don't think I want the area of the rectangle. There you go. Well, W squared plus, what's this right here? 1/2 L, right? So 1/2 L squared plus W squared equals 64. So 1/4 L squared plus W squared equals 64. So now it's up to you which one of these you want to solve for. Probably easier to solve for W squared. So that'd be 64 minus 1/4 L squared. This is a calculator one, right? Okay. So W has to be positive, so square root of 64 minus 1/4 L squared, and you cannot square root those, don't try. Okay, so your area is L times the square root of 64 minus 1/4 L squared. Now I'm curious what the answer book says. It's a calculator problem. So what could you do at this point? You could, well, okay. So if we're following what we learned, this is the area. Derivative, set it equal to 0. I'm thinking even a shorter cut to that, I'm thinking just graph that. Couldn't you graph that and see where it's a max? I mean, you know what I mean? That's one of those things we said you're not supposed to do, but this is a multiple choice question, right? And so if this is a free response question, that wouldn't be good enough. If this was a free response question, and so to be honest, on these reviews, I would prefer that you do A prime, write it down, set it equal to 0, do a solve. My guess is they don't maybe go through all that. What number was that? 42. Oh, no, they do. So they've got, they used a little different. They let this be, they let 2x be this base, and so they did area equals 2x times w, and then they just had x, and then they didn't get this fraction in there, which is not a big deal. But and then the other thing you got to make sure, if you do the derivative set it equal to 0, I think the one that you want is square root of 32, which is actually 4 times root 2. So you don't, but that would be the x value. That would be the, well, no, wait, they might have found a different one. Never mind.
I found that.
What do you got?
11.317.
The y value? No, the y value. See, you want the y value. It says, what's the maximum possible area of the rectangle? So if you graph this, you're looking for the biggest area, right? Now, where did it happen, right? That'd be the 11 point whatever, which I think would be 8 square root of 2, right? So I think if you do the derivative, set it equal to 0, solve, you get 8 square root of 2. Okay, so you gotta be careful. That's why they put that in there. Well, you don't want 8 square root of 2. That's where the max happens. They want to know what is the area, the max area. So you have to put 8 square root of 2 back into this, and you get 64. But if it's a multiple choice question, and they're asking me the max, once I get this, I think I'm graphing that, and I'm going to the highest point and looking at the y value. And the y value is 64. So the right answer is 64. Okay. But if you do the derivative, set it equal to 0, solve, you get 8 radical 2. You also get some other answers, don't you? Did you do the derivatives? Oh, you graphed it. Okay. If you do the derivative and set it equal to 0, I think you get like plus or minus 8. I think you get plus or minus 8. Well, maybe you don't get plus or minus 8. That's what they got in the book, but they used a different equation. So there's a, what's that? Yeah. But anyway, but the key is anytime you get these circle with something inscribed in it, right? You always want to go for a radius, right? Because you almost always know the radius of the circle. So you always want to draw that. Almost always ends up being a rectangle or a triangle in there, and the hypotenuse will be that radius. So you always want to get that involved somehow. And that's kind of the secret to that one. But that's good. That's good review of our finding a maximum optimization. We want to get it in terms of one variable. There's got to be some way in the picture and so forth to get that. Okay. All right. Well, let's move on here. Maybe we can do a few tomorrow again. Maybe if you get into the free response a little bit. If you haven't, you should be doing that. Let's go to our topic today here, which is the last thing in chapter 6. So let's probably get your notes out here, and let me find should have had this stuff ahead of time. All right, everybody grab your calculators too. You're going to need those. Matter of fact, you should put pants on. This is a fancy presentation. I actually stole this from somebody else who worked so hard as to do my own PowerPoints.
Do they have a math history?
Math history? Oh yeah, in college. Yeah, one of those things we used to do a little more of because of time, we've cut a few things out, but sometimes we should always incorporate more of that. Yeah, you can't yet, but so today's topic is related, as you will hopefully see today, is related to what we were doing with our rectangles and our error-bound formulas and so forth. And we'll be reviewing those things tomorrow. But and we, of course, we talked about the more rectangles you have, the better your approximation. We talked about how much your rectangles are off and why they're off. And of course, if you have more of them, they're not going to be off as much. But let me. Okay, now you should be able to log in. All right, let's. Why do I have? Oh, what is the teacher? Back, jeez, you always do something. All right, so. All right, so first of all, so this is pronounced, it's not Euler, it's Euler. I think I have talked about it before. His name is Euler. Euler's method. And again, we'll get a little history lesson on him a little bit, but he was, a famous mathematician. And what is Euler's method? Euler's method is a numerical method for solving differential equations. And again, what's a differential equation? No. It's an equation that has derivatives in it. It's not differentiable. That's different. When a function is differentiable, that's one thing. A differential equation is an equation, so it has an equal sign in it. It's an equation that's got derivatives in it. Okay? And what's the solution to a differential equation? The original equation, like y equals. So if you have y prime equals 3y, we'd be looking for y equals y prime equals 3x plus 2, y prime equals 2y minus 3x, y double prime. And it doesn't have to be y prime equals. You could have a differential equation that was 3x minus 2y double prime equals sine of y prime minus y squared. I mean, it doesn't have to be like a y prime equals, right, to be a differential equation. It's just any equation that's got derivatives in it. It can be a mixture of the input and the output variable, or what we call the dependent and the independent variable, okay? But in any of these, the solution is y equals blank, and then with just the x's in it, right, on the other side. So y equals, so that's the solution to a differential equation. So to review, remember we said slope fields were a graphical method for solving differential equations. So if we pull up, I'm not going to hand them out right now, but this is the 2014 AP test, okay? And so if I look at question number 6 on the 2014 AP test, here is a differential equation. Notice it's a mixture of x's and y's, okay? This is not one we know how to solve right now. In chapter 7, we're going to learn how to solve it. But it says let y equals f of x be the solution to that differential equation. Then they give you an initial condition. So that's the solution, the y equals, right, f of x, some x's. So y would be the solution. It says sketch the solution curve. It says a portion of the slope field for this is given below. So we talked about that. this is the graph of y. This is the solution. And so it says plot the one that goes through the initial condition 0, 1. So on the AP test, all you would do for this part is you would just come in here. Remember, we said we'll just kind of go through and kind of follow the slopes a little bit, kind of come down here, and now they kind of level off and so forth, and turn around, so forth. So this would kind of be, this would be your solution, and you get probably 1 point for sketching that in, okay? So maybe I should have leveled that off a little more here, a little lower in here maybe, but probably more like that, whatever, okay? But that's pretty rough. That's pretty rough. And it's better than what we used to do if we had a y prime graph. Remember, if we had an f prime graph, we could graph f by just kind of, it goes up for a while, and then it switches to down, and then it goes back up, and we were kind of guessing. At least here, we're kind of going with the flow, so we feel fairly confident. But if I ask you what's y of 2, how confident would we be in this y value right here? Not real confident, but even like here, you noticed how I went down here and then here. I mean, it could be off quite a bit, but it's not bad, okay? So a slope field is a way where we can plot these little slope segments based on our differential equation, and then we can kind of sketch in the y. So that's a graphical solution to a differential equation, a slope field. Okay, what we're looking at here, Euler's method, is a numerical method. A little more accurate, but takes a little more computation to do, okay? So let's say we had this differential equation right here. Let's plot ourselves a quick slope field on this one, okay? So let's do a quick slope field here, and so we would plug in some points. Remember, this is how we did this, because on the AP test, on our final, you may have to do this, and you may do it a little bit on this next quiz. Probably not, because we're not going to do slope fields on this quiz. On Thursday, we're going to stick with the stuff we've been working on. But just quickly to review. So what would I do? I'd plug in some numbers for y. So let's say y is a 0. What do you get? So what's that tell you to do here? Cross here, I'm going to put little horizontal slope segments. And remember how we talked about if only y is in the differential equation, then you're going to have these rows of slopes that are going to be the same, right? Because when we change to a new y, so when y is a 1, what happens? Slope of 3, which is pretty steep. So all the way along here, when y is 3, we're going to get a slope of 3, right? And then when y is 2, we're going to get a slope of 6, so it's going to be really steep, right? Really, really steep. I mean, it's hard to draw a slope of 6. It's almost vertical. Those aren't very good. And then -3, if you go down to y equals -1, you'd have slope of -3, right? So we'd have -3 down here. And so it's hard to draw a really good slope field of this. You almost need to get some points in between, like a slope. What would a y value, another y value to pick that wouldn't be bad? We have 0.5, or how about 1/3 even, right? Or 0.5, we can do 0.5. 3 times 0.5 is what, 1.5? So that's going to be a slope of 1.5. So in here, you would have slope of 1.5. Gives you, gives you a little more, just gives you some other points, and this would be -1.5, right? So not as steep, whatever. And so we could plot as many as we want in here, but we know it's horizontal down here. So it looks like you're going to have kind of an asymptote kind of a thing here, right? Now, actually, hopefully some of you recognize that isn't this one of that one we memorized, the solution? Y prime equals ky. What was the solution supposed to be? AE. In this case would be, k would be 3, right? AE to the kt, right? T is our input, so this would be our t-axis here, this would be our y-axis here. Oh, it's an exponential curve. Yeah, sure, it's an exponential curve, right? And if it was negative, you know, it'd be going down like that. Or if we had negative initial condition, we'd be down there, right? So it depends where our initial condition is. So it makes sense that it looks like that. It's an exponential graph, and we've got that horizontal asymptote down there at the x-axis. So it makes sense. So we kind of we've kind of done that. Like I said, if I throw in an initial condition here, we go y of 0 equals 1, then all of a sudden we could just draw in. We could come in here and we could say, okay, that's going up like that, and it's going to come down like that, and there's your solution, right? We just kind of follow the slopes. Okay, so that's a slope field. That's a graphical solution. But what we don't know, what we don't feel real good about is what if I ask you, what's y of 1? Okay, so here's my differential equation. Here's my initial condition. Give me some other points on y. Okay, so I've got this rough graph, but what would that be? What would you feel comfortable saying that y of 1 was? 2.5? It'd be pretty rough, right? It'd be pretty rough estimate. All right, so now let's go to our calculator. Okay, so let's go to Max here, and let's go to your graph. All of you can do this, so go to your graph and screen, and now let's go to your menu. Now clear out any other graphs you have already. Clear out any other graphs you might have. And I'll go to menu, and let's go to graph entry, and then let's go down to differential equation, number 8. And notice how different it looks. Now I think I've already showed you this. We did this with the slope field. So we got y1 prime equal, we want to do 3y. But we got to do 3. We can't just do 3y. Because it's y prime equals 3y. Well, this is y1 prime equals 3y1. So we got to type 3y1. You guys will have to do this on the quiz Thursday. You will have to type in a differential equation, and you're going to have to know that you're going to have to type y1 there. Or y2, whichever one it's in. You should just always put it in y1. Okay, now let's put our initial condition in here, which we said was 0, 1. And then let's hit enter. Okay, and there now. It's not a great looking slope field. It's not a great looking graph. Okay, but it's good enough for us. Right? Well, let's go to our window. Let's look at a couple things on the window. So let's go to window. Window settings. Now you're going to notice a couple things on this graph. Let's say I would probably give you certain windows. So let's go. Let's say -2 to 2, and then let's do a zoom fit. Hit OK. Oh, it looked like it adjusted it. Maybe it didn't really. But, oh yeah, I don't like that actually. So let's go back. Oh, right. Zoom fit. Oh yeah, zoom fit must not work as quite the same on this, so that's okay. Let's don't do zoom fit. I'll probably give you, if I need to, I'll give you a window. Probably won't need to actually. Let's go -2 to 2 again, and then just go -6 to 6, whatever it said before. It said -6 to 6 was fine. So let's do that. Okay, now let's trace, and let's go to 1, and let's see. We said on that graph I just did, I said 2.5. Okay, let's trace over to 1. Oh, yeah, I missed it pretty bad, right? My graph was not very good, right? Well, it made sense, because if we were at arrow back, okay, keep going, okay, keep going. Huh. Well, that makes sense. At 0, 1, the slope was 3. So if you move over a little bit, but then the slope was getting steeper, right? The higher up you went, the slope kept getting steeper. So yeah, my graph was off pretty bad. Okay. So if we trace at 1, it was like 13 something. Okay. So let's do a different. Let's do a little easier one to think about. So let's type in. Let's talk about this one right here. Let's talk about this one right here. Y prime equals 2x, okay? So back to your notes. We'll come back to the calculator here in a second. So let's say we have y prime equals 2x, because this would be one we could solve, right? Y prime equals 2x. Let me do it off to the side here. So y is going to equal what? x squared plus, well, you're jumping ahead, but you're right, it is going to be that. But normally we would just go x squared plus c, right? So remember this, why is this one we can solve and the other one wasn't? It's got an x in it, right? And so we can just do our antiderivative thing. When it had a y in it, we couldn't do that. If it's a mixture of x's and y's, we can't do that. But if it's just got x in it, we can just do our antiderivative. So x squared plus c, now let's put our initial condition in. So we put in a 1, so that would be, put in zeros, and that's got to equal 1, so it'd be 0 squared plus c is got to equal 1, so c is going to equal 1. So we know that the solution of this is going to be y equals x squared plus 1. So now you notice these are kind of what I'm going to talk about when we talk about Euler's method. Okay, so we're interested in figuring out, well, what's y of 2? Well, we know what y of 2 is going to be, right? Because we know what y is. This is an easy one. We can solve it. What's y of 2 going to be? Y of 2 is going to be 5, right? Y of 2 is going to be 5. We know that. Okay? Now, in Euler's method, it says use 4 steps to find y of 2, use 10 steps to find y of 2. Well, look, we're going to go back to the calculator. So let's go back to the calculator here. And you can do this on yours. And let's go ahead and put in our differential equation. So we got y1 prime equals 2x. Now notice we can use x here. A lot of times differential equations use t, but in the calculator you can tell by the initial condition here, it's got x and it's got y1. Okay, let's put our initial condition in of 0, 1. Okay, and let's hit enter. Okay, and we got to set our window because it's not giving us a good window here. So let's go say, well, -2 to 2 should be good. Let's do our y values from, we know it's x squared plus 1, so we know it's a parabola. Let's go 0 to 20 maybe. Why are we not getting this? Okay, so, all right, so here's what we're going to do. This guy I was not going to do this yet, but let's go back, hit tab, go back to your equation. Okay, so the key to us, arrow up, the key to us are these 3 little dots right here. Okay, so we need to either click on it or hit your tab until it highlights and then you can hit enter. Okay, here's what we need. So those 3 little dots, everybody got that? Everybody got this up on the screen right here? Okay, because you're going to have to be able to do this on the quiz. Okay, so Euler is what you want that to say. Does everybody say that? Emily, did you say that? Okay, we want it to say, and then 1 is fine, and then slope, keep arrow down, okay, keep arrow down, okay. Plot start, plot end, we don't have need those to change. Okay, the plot step here, okay, it says 0.1. Guys, that should be fun. Okay, what's that? Well, that's where it's going to check. So the key thing you'll have to change, so arrow back up here. So the only thing you'll ever have to change on your graphs after you get them set up with your initial condition or equation is you make sure this is Euler, and then we arrow all the way down, and that plot step is the only thing we should ever change. So right now, and then field resolution, make sure that says 14, which is okay. Okay, hit okay. Is anybody getting a graph to show up? Oh, now it's popping up. Okay. All right. So let's trace over to 2. And it's going to redraw the graph. Oh, and look what we get. We get 4.8. We don't get 5. Huh. Why don't we get 5? It's an approximation. It's using an Euler approximation, and it depends on that plot step. Now, if you trace backwards, go back to your left. Now, just go left arrow. Look what it's going by. 1.9, 1.8, 1.7, right? What's it going by? 0.1, which is what we put in there. So let's go back to your tab, and let's go back to that 3 dots, the settings. I call those the settings. Okay, let's go to there, open that up. And let's arrow down and let's call it 0.5. Let's do a plot step of 0.5. Now notice you have fewer dots, right? So it doesn't give you the solution curve. It's just giving you some points that it's estimating to be on the solution curve. Now let's trace over to 2. What would you expect now? It's worse. It's worse, right? It's farther away from 5. Now we get an approximation of 4. Okay, we're going to see how this is getting this here in a minute. But this is how, you know how I gave you that program? I said if you have 10 or more left rectangles or right rectangles to do, you can use this program if you want to do 50. Well, same thing's going to be true with Euler. If we're only doing a few, like on this one, there's just a few dots here, you're going to do them by hand. If there's a bunch of steps to do, you're going to trace on your calculator to see what the approximation is. So it's going to be similar.
So the actual answer is 5.
The actual answer is 5.
So the error on the first one was 2.
Yeah.
So
And,
the error is twice the once.
yeah. I suppose on this one it probably is, but that's probably just specific to this one. Yeah. And we're not going to really get into error, like how far off it is. We're just going to talk about why it's off. But it's kind of like rectangles. The more of them you do, it seems like the better off you'll be, right? But it's an approximation. So that's why this is not a bad time to talk about it, even though this doesn't have anything to do with area, doesn't have anything to do with integrals, doesn't have anything to do with rectangles and trapezoids. It has to do with solving differential equations, but it's a very similar process. It's an approximation, and the way we do it, and the answer we get, those rationales are all kind of the same. So on the quiz, if I say use 4 steps to find y of 2, we're going to write that out by hand. We're going to see how Euler's method works. If I say 10 steps, then you're going to type it in your calculator and trace over. Okay, so we're going to go through both of those right now. All right, so before we do that, don't forget about this. Remember, I may have you do this again tomorrow as part of a problem. So if I have y prime equals 2x and y of 0 equals 1, it says show that y equals x squared plus 1 is the exact solution. Remember the T-chart things we used to do, right? So on this side, y prime, well, if y is equal to x squared plus 1, what's y prime? 2x. So over here, we would substitute that. So we put a 2x right there. Oh, this is a really super easy one, right? It's easy to see that 2x equals 2x, but that's not quite all. The other thing you have to do, we did a few of these, not very many. Mostly when we did our t-table, we just stopped right here. But whenever you have an initial condition, you got to put that in too. So you got to show that y of 0 does equal 1. So you've got to put a 0 in here. So you got to go 0 squared plus 1. Oh yeah, okay. Y of 0 also equals 1, right? I mean, this initial condition has to work in here, and it has to work for that differential equation. So I may give you another one of those where I say verify that this is the solution, and we'll look at another one like that here in a minute. Okay, so back to this. So now to my fancy PowerPoint. Okay, so on my PowerPoint. All right. So Euler, Leonhard Euler, 1700s. Okay, kind of after Newton and Leibniz and those guys. They were more in the 1600s, mid to late 1600s. Okay, and is where a lot of the development of calculus and those things came along. So then he kind of built on some of what they did. Swiss mathematician. Okay. It was Euler who originated or popularized the following notation. So he didn't necessarily invent them all, but he used them, maybe got some of them from some others. But he was the one who kind of is credited with really making these become commonplace in mathematical notation. Function notation. Okay, kind of a big deal. Using E as the base of natural law. Using I for imaginary numbers, square root of -1. Using the sigma symbol for summation. And the calculus, like we talk about Leibniz with delta y, delta x, or it's his notation. So he was kind of instrumental in using that, and using the Greek letter pi to stand for the ratio between the circumference and diameter of a circle. So kind of notationally, he was kind of involved in or responsible for a lot of stuff that is that we use today. Okay, all right. This is fitting today. You know what today is? It's Pi Day, March 14th, 3/14. Well, or you could have brought me pie. Right? Probably should have. Correct. We should have had some pie. All right, so there are many differential equations that cannot be solved. We can still find an approximate solution. We will practice with an easy one that we can solve. So this is the one we just did. So y prime equals 2x. So we know the solution is supposed to be 5 if you were doing y of 2. Okay, so this is, okay, so I want you to write this down. This is going to be your first one. We're going to make, when I say you're going to write out Euler's method by hand, this is what I'm talking about right here. We're going to make a table of points, and this is how we're going to understand how Euler's method works. Okay? How does it's very related to a slope field. Remember, a slope field is based on the slopes. What are the slopes doing? Because the slopes tell you how much to go over and up. Right? That's what a slope does. Rise over run. Right? If you go over this much, you go up this much. If you go over this much, you go up this much. That's what slope tells us. Okay? So when we have a differential equation, we know the slope. So we're going to use that to tell us how much the graph goes up or down. That's what Euler's method is based on. Very simple idea. Very simple idea. So the end column I don't care about. So you can skip the end column. I don't care. I'm not even going to draw the end column. Okay? So you can just ignore the end column. So we're going to start with our initial conditions. So we're going to have an x column. We're going to have a y column. Now it could be t if your differential equation has t in it. It could be t, but that's your input, your output. So we're going to start with point 0, 1. The next thing, so we plot. Now they plot that. You don't have to plot it. But so that's where, this is my y graph right over here on the right. This is my y graph. Okay? All right, next thing we're going to do is get the slope. Now, where do you get the slope from? The differential equation. The differential equation gives you your slope. So we're going to plug into there, and you plug in a 0 and a 1. Well, there's no place to plug the 1, so we just plug in the 0 in for x, and we get a slope of 0. So that tells us at this point, the slope is 0. Okay, now, here's the key element. The next thing here is the key element that we usually will have already calculated when we're doing Euler's method. You'll see how it's connected to what we've done in the past. Okay, right here, dy over dx, which is rise over run, times dx, which is what? So this would be rise over run times run equals the rise. Oh, we did that the other day when we were doing that error formula. Remember we did that? We said the slope, we said we take the rise over run times the run, we get the rise. What's the same idea? That's all this is saying. Now, what's our run? Remember, we're trying to find y, they told us y of 0 is 1, and we're trying to find y of 2. So how far over do we want to go? How far over are we wanting to go from our starting point? We're wanting to go over 2, but that's our whole width, right? So the question then becomes, how many sub-intervals do we want to do? See the connection to rectangles? How many? That's where the step size come in. Remember it said the step size in your calculator? It said, didn't it say step size? Or plot step? Or plot step, is that what it was? Plot step. That's our what we call our step size. Well, remember back on my screen a minute ago, I said we're going to do 4 steps. We're going to do 4 steps, sometimes called 4 Euler steps. Okay, well, if we're going to go from 0 to 2, and we're going to do it in 4 steps, how much is each step? 0.5. Oh, that sounds familiar. Isn't that b minus a over n? Isn't that like finding our width, right? 2 minus 0 divided by 4. We're going to go from 0 to 2. Now, it's different because we were doing it before. We were doing integrals, and we were going 0 to 2. But now, it's very similar. We're starting at an x value of 0. We're wanting to go over here to 2, and we're wanting to see where we're at. So we're going to go over 2 as our total distance, but we're going to do it in 4 steps. So each one's going to be a half. So that's called our step size. So you'll usually figure that out right away in the beginning. So usually in the beginning, you'll figure out, or you'll be given your step size. So it might say, so the problem might say, find or estimate y of 2 using 4 Euler steps of size 1/2. Well, they wouldn't have had to tell you the 1/2. If they tell you to go from start with y of 0 and go over to y of 2, if they're telling you to go over 2 and to do 4 steps, you know you can calculate each one is 1/2. Same way we did our width of our rectangles. It's the same exact idea. Okay? All right. So they do the same thing. They just say dx. They call it dx, but we call it delta x or our width or whatever. That's our step size. So you had to be given originally that you were doing 4 steps, right? You have to be given that information so you know, or you had to be given the step size. Sometimes they'll say, use step size of 1/2 to estimate y of 2. Or it might say, use 4 steps to estimate y of 2. Either way, you can get the step size. So, what's that mean? That means the next thing in our column we want is that. Now, I would label that as my rise. I label it dy or delta y is fine. Label it delta y, but also think of that as your rise. Remember, this is your slope. This is your slope, which remember is rise over run. Rise over run. So to get this, what are you going to do? Let me write it in red. So this column, you're going to take your slope times your delta x. So to get this column right here, to get the rise column, you're going to take your slope, which is this column, times your step size, which you should already have calculated. Make sense? So you're going to get your slope from your differential equation. You're going to have your step size, which is how far over you're going. You multiply those two together, you're going to get your rise. Well, in this case, we're going to take 0 times 0.5. It's still going to be 0. So what's really going on? What's going on is we're saying, okay, we're starting here. The slope is 0. So if I go over 0.5, how much am I going up? 0. Right? That's what we're doing. So earlier, remember what I said. Euler's method is about figuring out the slope, which tells you how much to go over and up. And then, what we're going to do, so now that means we're going to go up 0. So what's my new y value? That's what this means. My new y, think of this as my new y right here. My new y is going to be my old y plus my rise. Make sense? So my new y is going to be my old y plus my rise. How much did I go up? I add on or subtract, whatever, how much I went up. That's what that's saying. So that's going to be my last column is my new y. So this column is my new y. Well, it's my old y. So again, if you want to write that down here, this column is going to be your old y plus your rise, which is the delta y, the column right there. So our old y was 1. We're going to add on a rise of 0. So our new y is 1. So we didn't go up at all. We didn't go up at all. So what point are we now at? No. How far did we go over? We only went over 0.5. So our new point, again, ignore this column over here. Ignore this column, the end column. I don't care about that column. That just confuses me. So our new point here is 0.51. So we went over 0.5, but we didn't go up at all. Why not? Because the slope was 0. Now the slope, though, here's the key thing. I know I've said that several times. The slope is only 0 right here, right, at 0, 1. As the graph goes this way, does the slope stay 0? No. As soon as you move off of x of 0, the slope's not 0 anymore. So the real y graph does what? Starts going up, right? But what are we assuming? We're assuming the slope stays 0 for the whole 0.5. Doesn't that sound like what we talked about with rectangles? Left rectangles assume the graph stays flat. Trapezoids assume the graph goes linear, right? So they're off. Well, this is going to be off. Because we figure out the slope at this point and we assume for the whole step size, the whole 0.5, we assume the slope stays 0 even though we know it's not good. Okay, so we keep going. So what's our next thing in our table? We need the slope. So we plug in a 0.5. 2 times 0.5 is 1. So we get a slope of 1. What do we do with that? What do we do with it? We take that times our step size, remember? And that's why it's good to have your columns highlighted here, or headlights, so you know what to do. You're going to have to memorize how to do this table, because on the quiz, you're going to recreate this. I'm going to give you a y prime. I'm going to give you a starting point. I'm going to give you an interval. I'm going to say find y of 2 using 4 steps, using 8 steps, whatever. If it's less than 10 steps, you're going to do it by hand, and you're going to make this table. So you're going to memorize this table. You've got to know how to make this table. Okay, so we're going to take our slope times our step size, because slope times step size is going to give us rise. So that's going to be 0.5. So what's my new y? My new y is the old y plus the rise. So 1.5, right? So I'm going to go over 0.5 and I'm going to go up 0.5. So my new y is 1.5. And so that gives me that point right there. So over 0.5, up 0.5. I'm always going over 0.5 in this problem, right? Because that's my step size. So I'm always going over 0.5. That's always my run. Okay, and then we do it again. How do we get the slope? Plug a 1 into the differential equation. Plug a 1 in for x, you get 2. We take our slope times our step size. 2 times 0.5 is 1. So that's my rise. So I'm going to go over 0.5 and I'm going to go up 1. So I'm now at 2.5. Because now I'm assuming the slope stays 1, or excuse me, the slope stays 2 this whole time. So it's going to go over 0.5 and up 1. That's a slope of 2. Over 0.5 and up 1 is going to be a slope of 2. So that takes me there, and I'm almost there. I've done 1, 2. Now that first line doesn't really count. I mean, so my first step was when I went to 0.5. So you're going to have 5 of these lines when you get done. Well, you actually don't have to do this last line because you're going to have it. So now we do our slope, so we plug in our 1.5, our x. Now, you know what I usually do on these tables? Once I figure out my step size, I usually fill in the x row or x column all the way down. So once I know my step size is 0.5 and I know I'm starting at 0, I usually go 0, 0.51, 1.52. And I write that all the way down till my ending. And I know I want to end at 2. So that way I'm not confused. I know my x, what my x's are going to be at the start. So I usually fill that column in all the way down when I start, once I know my step size. Okay, so now we put our 1.5 times 2 is a slope of 3. Okay, and then we take our slope times our step size. Slope times 0.5 is 1.5. So that's our rise. So now our old y is 1.5 plus our rise. So that means we're going to go over 0.5 and up 1.5, which is a slope of 3. And we end at 4. And we're really done at that point. Now, a lot of times we go down to this next row and we write it. But that's our new y, which is going to be at an x value of 2. So what we have found is what we were looking for, which was y of 2. We were looking for y of 2, and Max did that for us on the calculator. He showed us that we got 4, remember? But you're really supposed to get what? We know we're really supposed to get 5, and here they draw it in here. Okay? We know the exact solution is x squared plus c. We find the c value, which we already did. We know the exact solution's at. Well, why is ours up? Well, because we assumed for this whole first step we had a slope of 0 when clearly it was starting to go up. And so we were behind already from there. Okay? And so that's why on your calculator when it plots, that's why on your calculator you don't see these lines. On your calculator you just see this point, this point, this point, this point, and this point. You just see those points. It doesn't give you the in-between stuff because it didn't calculate those. So that's why it doesn't give you a smooth curve for your solution. It just gives you a bunch of dots because we're using the Euler method to calculate that. Okay? That's called Euler's method. It's more accurate if you use a smaller width. Obviously, if you use more steps, just like with rectangles, it's less accurate as you move away from the initial condition because whatever error you have is just magnified and you know you're off and you're never going to get back on. And then this is Euler's method is built in. So if we had an example here, we're going to do a different example, but we just went through this with the graph entry. We type in our differential equation. I wonder how I can get those on the bottom. That's interesting. I don't know how that. I wonder if that's in the settings or something. So notice they use y1. Notice they use y1 in there. We put in our initial condition. We get our slope field, okay, and then you can trace. We'll just go through. We just talked about this, adjusting the window settings. So they went through this one, and you can try different initial conditions. So you can get several. If you click on that little thing, you can do several initial conditions. So you get a couple of different graphs all on the same page. But and then we can trace. And you can grab the point and drag the trace point, but usually you're only interested in a couple different points. so it doesn't matter. Okay? The book refers to an improved Euler's method, not our book, but whoever made this PowerPoint. On your calculator, there's something called the Runge-Kutta method. Think of that as the kind of this Simpsons rule. Think of Euler's method as kind of left rectangles, and think of Runge-Kutta as like Simpsons. It's better, does a better approximation, but it's a lot more complicated in how it works. Okay, so that's so Max, if you want to go back to that on your calculator, if you just want to hit tab and get back to your equation, and then go to the three dots, go to those settings, and if you go to your right arrow right there, and then you got that other option right there. But we won't use that. But if you go to that right now, if you just go to that right now, and leave that error tolerance what it is, I'm not sure that's how you set what you want. Now trace. Now trace over to 2. Right? I mean, I have no idea. No. But again, think of it like it's like Simpsons rule. It's just it's in the sense that it uses more advanced information, better information, based on what you know about differential equations to help you get to it. But it's not as easy of a process to understand. Assuming I've never worked with it. We didn't have the calculator computing power when I took this class to be able to even talk about it or see it. So, but yeah, it'd be an interesting thing to look at, I guess, and see exactly what's involved with it. But go ahead, Max, and go back to yours. Make sure it's set on Euler, because whatever we do, whatever tracing we do in our calculator, we want to make sure we're on Euler's method there. Okay?
Just shut the other one.
Right arrow up there. And then go down, arrow down. So, and then so the key part you're going to want to use in here is just that plot step. So now, we had said, remember we had got 0.8 before, so we just went through our 4 steps and we found y of 2 to be 4. I shouldn't say equals, I should say approximately 4, right? So we just went through and did 4 steps. Now, if I tell you to do 10 steps, automatically that means you get to use your calculator, right? So what do you need to calculate? All you need to do is do the 2 minus 0 divided by 10, which is 2/10, 1/5, or 0.2. We probably use decimals here. So that would tell you your step size is going to be 0.2. So you would go to your calculator. So let's do it. So we would go to our calculator. We would go into our 3 dots. We would set our plot step to 0.2. So that's the key number you're going to need using your calculator. You got to be able to plug in your differential equation, but you're going to calculate your step size, and that goes right there for plot step. So go ahead and hit OK. And then you get more dots, obviously, and now let's trace over to 2, and there you get 4.6. So all you would give me for an answer, so on the test, if it says use 10 steps to find y of 2, all you would give me is y of 2 is approximately 4.6. Okay? This was not as good an approximation as this, and of course we know the exact answer is that. Okay? But much like Aaron, you do 10 rectangles, you're going to get one approximation. You do 100 rectangles, you're going to get a better approximation. And of course, the definite integral is the exact answer. So, very close connection here to what's going on. Euler's method is not on the AP test. You won't notice Euler's method in any of these, but it will be. Wait, is it this year's test that Euler's method might be on? It might be on this year's test. It's not going to be on our final, just because I'm pulling from older questions, and I haven't seen any of their Euler's method questions. But now that I think about it, I think this year is the first year for the new test, because we talked about the different amounts of questions and stuff. So I think Euler's method is on the test this year. So if you are taking an AP test, we need to know. Okay, last question. Let's run through this. This will be good practice, because you're going to get asked some questions about this in your homework, I think. Okay, so get your calculators ready to go. We're not gonna type it in, but let's say we wanted to do 5 steps, I told you. let's say I told you in this problem we're going to do 5 steps. This is a Newton's law of cooling, by the way. Remember when we talked about Newton's law of cooling? We talked about that, right? I got some hot coffee that's 190 degrees Fahrenheit at the start. We're in a 70-degree temperature room. Here's our Newton's law of cooling. What's the temperature 5 minutes later? What's the temperature 5 minutes later? So we're going to start with an initial condition of 0, 190. Okay? So then we have to calculate our slope. So just be on your calculator screen is the only place you need to be right now. Okay? All right, so how are we going to get Y5? Oh, okay, very good. I should have done that right away. So we're going 5 minus 0 divided by 5. So our run, our delta x is 5. So I would actually write that down right away right here. I would go right down to here and do this, right? Just so I don't get confused on that column, we're going to know right there. 0, 1, 2, 3, 4, 5. Okay? All right. So yes, that's good. So I needed that. Now what's my y prime? What do I plug in? Plug in a y. So I need the 190. 190 minus 70 is 120. What's 120 times negative 0.1? Negative 12. What's my rise? I change in y. We take our slope times, right? Slope times run gives you rise. What is that? Oh, because it's, what's our step size? 1. So, negative 12, right? Our step size here is 1. So we're going to take our slope times 1. So our new y is 178. What does that tell us in the coffee problem? So it went down in 1 minute, it went down 12. But again, we know that that's assuming what? That the slope stayed negative 12 the whole way. Probably did, right? Coffee cooling starts to kind of slow down and level off, right? So it probably didn't cool down 12 degrees in that whole minute. But this is what we get, okay? How do you get your y prime? You got your y prime equation right here. Well, it's y. In the last problem we did, it was x. So we plugged in our x. But this problem, it's y. So we can put your y. It depends what's in here. And you could get a difference equation that's got both x and y. If it's got both x and y, you put the x where the x is, you put the y where the y is. Right. Okay, so now we put our 178 in for y. So we get what? 108? So negative 10.8. So we're going to start getting some decimals here, right? And so now we're going to take that times 1, so that helps. Now, if you get into a problem with some messy decimals, you only write down 2 or 3 is fine, but you better keep, right? You better keep all of them in your calculator. So every time you do a multiply by the step and you add on to get your new y, and then you write it down here, you only have to write down a few decimals in your table, but keep them all in your calculator so you're not getting rounding error. Okay, so then we take that times our 1, so that's easy. These two are the same, and that's just because we're timesing by 1 here. Our step size is 1, so whenever we multiply by 1, right, we're moving over 1 each time, so we're going to go down 10.8, so that's what, 167, excuse me, 167.2. Then we're going to plug that into there, 167.2 minus 70, 97.2 negative.
No, point negative.
Negative 9.72. So negative 9.72 here also. And then we're going to go down. Let's do one. Let's just do this one. And then we're going to cheat and go to our calculator real quick. So what's that? 157. I think it'll be 156 point 157.48. 156, isn't it?
Yeah. Oh, yeah, cause it's one.
Oh, it's less than 10, isn't it?
You're not rounding the students, rounding.
Yeah, if it went down 10, it'd be 157.2. It's going down less than 10. So. Okay? All right. So let's stop right there. And we could, let's cheat now and go to our calculator. So Max, go ahead and put that in. So we got negative 0.1. Don't forget you got to do Y1. You got to do Y1. It's very common mistake. If you got Y in there, you got to do Y1 there.
What
Okay?
happens if you don't put?
Well, it won't give you the right answer. And you can try it. It'll, I don't know if it'll give you an error, but it'll do something weird. It won't be good. So what's our step? We got to change our plot step. So you got really three things. You got to put in your differential equation. You got to put in your initial condition. And then you got to go to those three dots. You got to change your plot step. In this case, our plot step would be 1. And then you may have to change your window, but probably you can trace. You might be able to trace. We just want to go to 5. Maybe you can trace outside your window. Can you type in a 5? Without actually, because I don't care what the graph looks like. I don't care. Yeah, it says it exceeds the range, so go ahead and set your window. So you're going to have to go set your window to 0 to 5 at least, so you can trace out to there. All I care about is that value, right? All we care about is that when you're doing this graphing piece, all your hit OK.
You put your Y1.
I just.
Go set your window again. Hit escape. Go to your window. Yeah. Hit enter. And hit enter. Now hit escape. Hit escape. Hit escape. So you're still in the trace mode. Okay, now go to your window. Now go to your trace. It might be because your Y window's not. There you go. 140.859. That's not what you got. Yeah, 0.190. Yeah, 0.190. So 140.859. So once we get down to here, right, at the end of here, we'll have 140.859. So 140.859. So that's saying that it's down to 140 degrees. Now it's probably down not that much because we know this level's off more. Ours went down 12, and it probably went down too much. So it probably is not that much, but we can fix that. We can change.
I put it.
What's that?
It wasn't like loading the entire graph, so we have trace the 5.
Yeah, I mean, we could go to your window. If we want a little better graph here, we could go window. Okay, let's go window settings. Let's start at an X of 0. Let's go out to 10 minutes, let's say. Let's do a Y of, we're going to go down probably room temperature 70. So let's go 60 is our minimum. And it started at 190, so let's go 200. So our Y is our temperature. So we can make it through, and we can, okay. And so arrow back. There's 4, arrow back again. There's 3. Why isn't there a dot there? It's kind of funny. There's not dots there. I'm not quite sure what's going on there. But anyway, arrow back another one. So you see how those are numbers we had? If you arrow back one more. Did you? It's not doing it. Okay. You notice, I think that was a number we had. Didn't we have 167.2? Do a right arrow 1. Left arrow. 3 we had gotten 157. Oop, go back. Go right. I mean, go to 3. There you go. 157.48. Yeah, it's lagging here a little bit. But that was a number we just had, right? So if we'd have gotten, and I'd go to the right. And then if we'd have done 4, we'd have gotten that one, and then go 5, and we'd have got that point, that next point right there. Okay? So if I said do 10 steps, now they'd be step size of 0.5, so you go in and change your plot step to that. Okay? So that's what a table on that looks like. And then the last thing, show that. So then this says show that this is a solution. Okay? Show that this is a solution to this. So remember how we did that? And remember it said y of 0 is 190. So we would do y prime of this. So the derivative of 70 would disappear. The 120 would just stay put. e to the negative 0.1t is its own derivative times, you kick out a negative 0.1, right? If you take negative 0.1 times 120, you get negative 12 e to the negative 0.1t, like that. That would be your y prime, right? What do we get on this side? We get 0.1 negative, and then we get our y, which was 70 plus 120 e to the negative 0.1t. That's our y, and then minus 70, right? Oh, look what happens. The 70s will cancel. We get negative 0.1 times 120 e to the negative 0.1t. Sure enough, when we multiply that, we get negative 12 e to the negative 0.1t, and that checks. And then also in red here, we would have to plug in our 0. So we plug in our 0 here, we would get 70 plus 120 e to the 0, which of course is 190 because e to the 0 is 1. So 70 plus 120 does equal 190. So we'd have to have both parts of that to verify that it is actually the solution. Okay, so that is the solution because it fits the initial condition and it fits the differential equation. And we did that little t-chart to plug that in. Because remember, this is our solution. We always take our solution and plug it into the differential equation. That's how we show that it is actually a solution. Okay? And so now we could, what is technically y of 5, so Max, do one last thing, put a 5 in there, right? We want to know how hot is actually the coffee at 5 minutes. We would plug a 5 into this, right? Because that is our solution of this Newton's law cooling problem. So we would plug a 5 into there. $142.784. What did I say? 142.784 degrees is actually how hot the coffee was. Back here we had 140.859, right? And so doing Euler's method with 5 steps, we were too low because we started at 190 and we went down 12 and then we went here and then we went here and then we went here, when in actuality it was going down less than that, right? It was going in a smooth curve, but we were doing an estimate. So Euler's method is an estimate, very much like rectangles are an estimate. Euler's method is an estimate to solving a differential equation. All right, so your homework is that last set of exercises on 6.3, which is going to be some practice. Again, if it says, well, let me just open it up here real quick. As your,
You have to like look at examples.
yeah, well, that's what I'm saying. In 1 and 2 and 3 and 4, it talks about example 1. Well, guess what? That's this problem we just did here, right? This is example 1. So in the first couple exercises, 1 and 2, it talks about example 1. But then 6 and 8 talk about some different ones, and again, they talk about a few number of steps. So you're going to do your table on ones like that. 11 asks you to do 5 steps in part A, so you're going to do those by hand, you're going to do the table, and then it says 10 steps, so you're going to just type it in your calculator and trace, okay, when it says 10. Then it says show the exact solution, and that's kind of what we just did on that one. Okay, so 11 is like that, 13. Now 13 in part A, it says use 10 steps, and then it says use 20 steps, so both of those you get to use your calculator, right? If it's double-digit steps, automatically get to use your calculator. And then in 15, part A says do 4 steps, so you're going to do your table, right, when it says 4 steps. And then it talks about the exact solution, whatever. So they're all very kind of similar kinds of situations. Did anybody leave their book here? No, obviously somebody left it.
I believe it's
Yeah. Somebody left the book at this point. All right, again, if you got that Niobrara thing, you finished at any time this week, you want to bring it in. just to get it out of your hair, that's fine. But it's due.
How far in are you on that?